Last time we continued the discussion of this general linear hypothesis test. And so the idea was to see if we have to be able to test, let's say, a null hypothesis that there is a certain linear set of constraints on beta in the usual regression model. And we saw that this general additional sum of squares test has a very nice geometric sort of interpretation that what you end up doing is that you project your response into the image of X or L of X. And that's like fitting the full model, the original regression model. And then under these constraints, the assumption is equivalent to the mu being the true mean of the regression model. The null hypothesis puts the assumption that mu is in a restricted subspace of the LA of X, which is this mu belongs to L of X. Under this assumption, you can see that it's of this form X beta, but under the null, under H naught, it would further belong to LA of X, which is a subset of L of X. And but by doing this projection once onto the L of X, we get the mu hat, and then once into the LA of X, we get mu hat A, we can then compare the size of mu hat to mu hat A, and if the difference is not too big, then we can say that. So if the difference is not too big, then we can say that the null probably is good, or we're under the null, so we don't reject the null. If the difference is too big, then we reject the null, and we saw that we can we have a result that allows us to form this F statistic. I'm not going to go into details again. We talked about this a couple of times, which is just the ratio of the size of this vector squared divided by Q, and then the size of the residual in the original model divided by, so this is the degrees of freedom of this, and this is the degrees of freedom of this. Both of these, if you divide by sigma squared, they have chi squared with the corresponding degrees of freedom. And so we divide them, and they're independent by this second half of this theorem. And so the result is an F statistic, so we can compare. So you evaluate this in a particular problem, and then compare it to the quantiles of the F distribution of the corresponding degrees. And that gives you a way to compute p-values. It just gives you a way to do a proper test at a certain level. So if I want a certain level, I can compare it with the quantiles of one of this F distribution at level 1 minus alpha, and so on. So now, so this was clear, right? And there was some sort of an alternative version that we discussed. So there's a lot of orthogonality going on in this picture. So by looking at this triangle, you can see that we can write the size of E squared is the size of plus the size of this squared is equal to the size of EA squared. This is the residual sum of squares for the restricted model. This is the residual sum of squares for the full model. And so we can compute this additional sum of squares by the difference between the two. And because this is always non-negative, you can see that the SSE, sum of squares of errors, or sum squares, residual sum squared or sum squares of errors, already called RSS or SSE. We're going to call it. We're going to call it SSE. This guy is always bigger than this. So, and there's some intuition behind that. The restricted model has less degrees of freedom. It's a proper subset of the full model. So when you fit it, you get less degrees of freedom to fit, and so your residual sum squares will be bigger. And depending on basically computing the size of this is comparing the sizes of these two SSEs. So if they're very close, then you would not reject. If they're different, then you would reject. So this gives you an alternative way of computing this. There are other orthogonality relations in this figure as well. So for example, something that came up in the midterm, I saw a couple of people ask that question. So how do you compute, for example, this guy if you're given just the norm of y and x and beta hat, but not y itself? So x beta hat would give you this mu hat, right? And you can see from the figure, because we're in this triangle, so you'd have this is equal to y squared is equal to this plus mu hat squared. So given this and this, you should be able to compute this. This all follows from the fact that E is orthogonal to mu hat. Another way, just you can directly do it. This is like E plus mu hat. You get E squared plus mu hat squared plus twice E times mu hat, and this is 0. Because E is orthogonal to mu hat. E is orthogonal to everything in the image. So these geometric ideas help you calculate certain quantities that might otherwise be difficult to calculate. Okay, any questions, comments about this? So this was just a review, basically. Questions? So we did this example last time that you would do that an experiment to compare the effects of certain drugs. So we have 5, let's say, drugs, and we give each group of people one of these drugs, and then measure the initial and the final cholesterol load. So the initial level is Z, the final level is Y, and then we can model the effects of the drugs as a regression where these are indicator variables. So Xi collects these let's see. So Xij is equal to 1 if subject I is took drug J, and otherwise, then when you write down the model like this, for every subject, one of these is only equal to 1, and this means that the coefficient can be interpreted as the effect of that particular drug. So if the subject I took drug 2, for example, the response would be a function of the initial, a linear function at the initial level plus beta 2. So you can interpret beta 2 as the effect that the drug has, like a constant effect on the final level. And with that formulation, we saw that you can write it in vector form. These would be indicator vectors. And so the vector would be all ones for group 1 and 0 elsewhere. This one would be all ones for group 2 and elsewhere 0, and so on. And then you saw that, for example, when you try to fit, to do a test of whether all these components are equal. Sorry, let's say this one. You're trying to do a test that all these betas are the same. This is testing for the equality of the effect of the drugs, that would be effectively solving a regression where I set all these betas equal to some gamma. The problem reduces to this regression model, where when I sum these all these guys, they get 1. And if I further try to test, so this we called model M1, let's say, and then if I want to test whether all of them actually have any effect, I can test this, whether they are equal and equals 0. That would be setting all the betas equal to 0. So the regression model just reduces to y equal alpha z plus epsilon. And so we did the tests, and there was this idea that we have actually 3 models. When you do an F-test for testing the hypothesis that all drugs are equal, you're effectively comparing these 2 models. The one is the full model, and the second one is the model that just sets all of these equal to, let's say, gamma. That would reduce it to this model. So model M reduces to M1 under assumption, the first hypothesis assumption, or the first hypothesis. Under the second hypothesis, model 1 reduces to model 2, where you set all the betas equal to 0. And so this was an F-test that we did. The first was an F-test that we did between the 2, and we failed to reject the null. So in comparing, you can think of the F-test as comparing these 2, and we failed to reject the null. So this was the null model. So we are going with this. If you compare M1 and M, we reject M in favor of M1, basically. Then we did the comparison, did the hypothesis that all of betas are 0. So we're comparing these 2. And in this case, we rejected the null. So we go between these 2, we favor M. And so this sort of, up to this point, it seems like everything points to model M1. So if I choose between M and M, if I want to choose between M2 and M, I have to go with M. If I want to choose between M1 and M, I have to go with M1. So we're at M1. There was another possible test that we could do between these 2. And this is actually a valid F-test. Anyone remembers why we can do an F-test between these 2? Maybe I should ask so that you guys can also participate. This is all like recap of the previous lecture. So why can I do an F-test to compare M1 and M2? Anyone? To see if you guys are awake.
Because we can compute the difference in error.
You can compute the difference in error between any 2 models. Penny has the right answer, but if you haven't looked at the chat, anyone else has the right answer? Just being able to compare the errors is not enough. The key is that M2 is nested. That's the key point. M2 is nested within M1. Or in other words, M2 is a submodel of M1. So this is key for being able to do an F-test. That being a submodel of being nested means that I can get M2 from M1 by setting some constraints on the parameters. So if I constrain the parameters of this, I can get this. And this is indeed the case. The only constraint that I need to put is that gamma is 0. This is a very trivial constraint. But by setting gamma equal to 0 in this model, I get this. So M2 is nested within M1. And so we can do a proper F-test. And for that test, the full model would be this. The null would be this. So we're comparing this null against this full model. So you fit this. The residual sum of squares would be going there, and the degrees of freedom of it goes there. And then the difference between the residual sum of squares of the 2, that's the additional sum of squares, goes there. And the degrees of freedom is the number of constraints that we need to put to get from this model to that, which is just 1. I said gamma equal to 0, that's a linear one linear constraint. And so this allows us to perform this test. And it turns out that if we did it correctly, that we also reject M2. So reject M2 in favor of M1. So everything correctly points to M1. Okay. Questions? So can you give me an example of the case where two models are not nested, and so we can't do an F-test? What would be an example where the two models are not nested? Anyone? So say M1 was y equal alpha z plus gamma 1n plus epsilon. M2 was y equal alpha z plus epsilon. Right. How about this model? Let's say M3. Alpha z plus 1n. Is this a submodel of M1? What do you guys think? Is it a submodel? Let's see, how about M4? Y is gamma 1n plus epsilon. Is this a submodel of M1? Are you guys there? This is M1.
It is.
Why?
Because all the terms in M4 are in M1.
Sorry, can you say that again?
So all the terms that are in M4 also exist in M1.
Okay, another way of saying it is that I can get M4 is just M1 with gamma or alpha set to 0. Okay, so I put a restriction on alpha and I get that. So how about this? Is M3 a submodel? M4 is, M3 isn't. Okay, so Brandon says M3 is not a submodel. So maybe you want to argue? Why?
Maybe if gamma is equal to alpha, then it's a submodel.
Okay, so yeah, so what we were saying here is any linear constraints, at least M3 can be obtained as M1 with the constraint that gamma is equal to alpha. This is a valid constraint. And in fact, when I'm talking about submodels in this course, I usually mean linear constraints. So you could have like other nonlinear constraints that would still be a submodel, but we can't do an F-test with that. But here, this is a linear constraint. This is equivalent to just one of these things that we had, right? So it's a linear constraint on the parameters of the original model. And so this is a valid submodel. And so I can compare M3 to M1. the only thing that I need to know is to fit this and then compute the residual sum of squares, and then compare it with that. And that's just testing this null hypothesis in M1. Okay, so if I want to test this null hypothesis in M1, that's equivalent to doing an F-test between M1 and M2. So what is an example which is not a submodel? So for example, consider M5, which is y is equal to, or just okay, we have M4. So relation of M4 and M2. Can we say that M2, look at this and this, is there a submodel relation between them? Can I say one is a submodel of the other? No? Okay, so neither is a submodel of the other. And so I cannot directly compare them using an F-test. And for example, I can't know about SSEF M2, SSEF M1. If I compare the SSEs, I can't say whether one is bigger than the other. Whereas when I compare the SSEs of the submodels, I can always say this is bigger than or equal to. Sorry, the other way around. So the submodel always has a bigger SSE. So SSE of M1 is going to be strictly or less than or equal to SSE of M2. Similarly, SSE of, sorry, this is 4. SSE of M1 is again less than or equal to the SSE of M4. And SSE of M3 is also, whenever you have a submodel relation, the SSEs would be respecting that order. Okay, SSE of M3 is also bigger. So all the submodels, the SSEs are bigger than the original model. But here we can't. So SSE of M1 and SSE of M2 are not comparable. Comparable a priori. Without fitting them, I can't say for sure which one is smaller. And we can't do an F-test. We can't do an F-test comparing M1 and M2. Okay? Sounds good? So these ideas are about F-tests as comparing two models. It's very useful to think about that. Is it clear to people? So forget about these a little bit. These are not some details that may or may not be interesting to you guys. So to summarize, there is some sort of an interesting relation between statistical concepts related to linear regression and linear algebra. So the subspaces in the linear algebra corresponds to models of the mean of the vector. So here y is like mu plus epsilon. So models for mu. So the regression sort of says that mu belongs to L of x, and then under the further general linear hypothesis, you're assuming that mu is actually in this subspace. The relation of submodel being nested, like models being nested within each other or being submodels of each other, is equivalent to this subspace relation. So this is saying the model associated with this is nested within that model, and so the subspaces, I mean, are subspaces of each other, subsets of each other. Fitting a model would be equivalent to projecting onto a subspace. I hope this is clear by now. At least this is fitting the linear model. This is linear. Okay, and then the unexplained variation by the model, you can say it's just the residual sum of squares of the errors of the projection. So this is also, so this has some intuition in terms of the statistics. So this is part of the, you can see from that relation that we just had. This is by Pythagorean theorem. So the variation or the size of this can be decomposed into two pieces. One is this part, which is related to the regression. So regression explains this. And this is the part that's not, the remaining variation y that's not unexplained. So this is like a decomposition of variation when you do the projection, decomposition of the variation in the response into pieces that are explained by the model, pieces that are not explained by the model. Okay. Questions? Okay, so if you understand this example, I encourage you to go through this example and try to understand this better. Both of these hypotheses that we did I mean, can be general. I mean, the setup that we have already is general, but these problems that we did occur very frequently. So the testing for equality of these when the x's are indicators, this is an example of a comparison of treatments experiment. So you have multiple treatments and you want to see whether they all have the same effect. So you model the problem as, you may not have this term, you just have these 5 drugs, you give them to people and then measure the response and want to see whether the responses are the same or not. And so you'd have a regression which has this part and the xi's are indicators. I'm going to show you some slides for the general formulation. The details you can figure out yourself. And then the other example where we set all of them equal to 0, that's also a very common problem. That's sometimes called ANOVA. The previous one is also called ANOVA. And all of these F tests are called ANOVA, basically. But your book also sort of emphasizes ANOVA is like testing whether these are 0. Although I don't want to call it that. Like ANOVA is all of these decompositions. But when you have a regression, so let's go back. Sets of slides. So analysis of variance or ANOVA, as your book calls it, is just a special case where you have a linear regression. Let's say you have a intercept. You have an intercept, and then you have these covariates. This is our general setup, and your null hypothesis to test whether all these betas are 0, the ones except the intercept. So the reason why this is interesting is that the intercept is like the default. You should always include it sort of to get rid of the mean of y. But beyond that, this is the part that actually models the relation between x and y. And so if this part is 0, it means that there's no relation between x and y. So you want to see whether this y, the response, and this set of covariates have any relation. If you're trying to test that, then you test whether all these betas except the beta naught are 0. So the null model, or the restricted model in this case, would be just this. So we refer, let's say, right, the simple model as m naught. So that would be m naught. And then the full model as m1. So testing the hypothesis, testing or comparing these two models. This is sometimes also called testing for the significance of testing for the significance of the linear model or the linear relation. When you do a significance test, sometimes that's the meaning. So how do we do this test? Just like any other general linear hypothesis test, I have to fit this model. And then compute the F statistic, which I can do by let's say by this principle that I can compute this additional sum of squares as the difference between the two SSEs. So when I fit the, anyone knows what happens when I fit the restricted model? So what happens? So what is the fitting the restricted / null model? Which is M naught. So let's say the LSE of beta 0 in M1 or M0, they call it beta hat 0. What is the estimate of beta 0 in this model? The least squares estimate. How do we obtain that? Anyone?
You just use like the formula xdx inverse xdy, where x is like the vector 1s.
Great, yeah. So this is exactly the same formula. So let's call this y1n. So this is x transpose. So x here is this. So inverse 1 transpose y. So does this simplify? The design matrix x is just equal 1n. Okay. So can we simplify further? So what is the dimension of 1 transpose 1n? Or what is 1 transpose 1n? 1n transpose 1n. 1. Okay, one idea is that this is equal to 1. Any other guess? N? Okay. Which one is correct? 1 or n? How do we compute it? This is just summation I from 1 to n. All the elements of this times the elements of that. All of them are equal, so you get n times that, so you get n. Okay, so this is one dimensional, so you get basically 1 n transpose 1 n inverse. And then you get 1 n transpose y. So this is, sorry, this just gonna be n, right? What is 1 n transpose y? The sum of the elements. Okay, so this would be sum yi over n. So this would be y bar. We call it y bar. So you can see that in this model, when you do the least squares, the beta 0 is just the average of the elements of y, which is very natural. Okay, the average of the elements. So on a side note, projecting onto or let's say, yeah, projecting onto a span of U, like a single vector, if you have a single vector, is equivalent to doing this. It's like minimizing, let's say y minus projecting y. Alpha U, minimize over alpha. And so alpha hat would be just U transpose U inverse U transpose Y. And the projection would be alpha hat U, which is U, that's the projection matrix, right? U transpose Y. And this simplifies a little bit for the case of when this is a vector, because this is a scalar, you get u transpose y divided by u transpose u, or u transpose y divided by us squared. And this is also going to simplify, like u transpose divided by us squared. This is us squared. So these formulas are helpful. This is the H matrix for H matrix for projecting onto span of U, and this would have been useful. You could have tried these yourself using. So this would be useful in the midterm. But this is nothing but a very special case of the things that we discussed. Okay, but it's good to remember for future, in case you wanted to project onto a vector. You can multiply the vector by this matrix, which is a projection matrix, and it's a rank 1 projection matrix. Rank 1, rank equal 1, because you're projecting onto a subspace of dimension 1. And whenever you do like a regression with just a single covariate, that's the form of the this, like the estimator, the LSC. Okay. So that was the detour. So now what is the we have computed this. What is the SSE for M0, which is, we usually write it as this. So this is SSE of M0. So what would it be given these calculations? Let me help you. It's going to be y minus, this formula is easier to use in this case. That's the mu hat in this model. That's y. So what is this simplify to? Anyone? Can you expand this? Summation I from 1 to n. yi minus beta hat 0, because this is just a vector that has all the entries beta hat 0. And beta hat 0 is y bar. So this is just taking the deviation y minus y bar squared. Okay, so this might look familiar to people. This is also called the SSE, sorry, SST. So the SSE of this null model is called the total sum of squares, or sum of squares. Sum of squares total. So this is the total variation of y around its sort of empirical mean. So this is good to remember. It's just the SSE of this simple model, which is just putting an intercept there. So this is generally called SST. And then the F test, and then we have SSE of the full model would be just E squared, which is just, I mean, you can have different formulas, it doesn't matter. Beta hat, say X beta hat, or there are other formulas. You know how to compute this. There's no like simple way of doing it, but let's call it, sorry, we called it MP. We call it MP here. And so how do we write the F statistic to do the hypothesis test? So F statistic for, so what is the F stats for comparing MP and M1, i.e. Testing the null that beta 1 is equal to beta 2 is equal to beta p is equal to 0 in MP. So what is the test statistic for this? What is the numerator? What is the denominator? Okay, SSEF M naught minus SSEF MP divided by degrees of freedom is Q. So what is Q? You have to figure out. And then SSEF divided by SSEF MP, yes, that's the full model, divided by N minus D. Yeah, D is P plus 1. Because we have P plus 1 parameters here. That's true, but what is Q here? The number of, that's the number of independent constraints that we're putting to get from MP to, sorry, M0. This is M0. Or the number of independent constraints here. How many independent constraints do we have?
Is it P?
Sorry, can you say it again?
Is it P?
P, yes, that's P. If you go back to the discussion, I mean, it should be clear. So we had like 5 Greg's example, that would be 5. We talked about that. Okay, so that would be, and this guy is SST, okay? And this is sometimes just referred to as SSE. So you'd get SST minus SSE divided by P divided by SSE divided by N minus D, okay? And then you compare it with an F, the statistic of degrees with a P and minus D. So this is sometimes referred to, this difference is sometimes referred to as the SSR, okay? And we have the decomposition SST is SSE plus SSR. This is nothing but these decompositions that we have. This is like EA squared is equal to E squared plus nu hat minus nu hat A. So that's the orthogonality principle that we discussed. So this is called regression of sum of squares. Then we have SST. And then oftentimes you write this in an ANOVA table. So SST would be this, SSE would be the SSE of the full model, SSR is the difference. There are alternative formulas for this. You don't have to remember. You can drive everything yourself if you want. And this has P degrees of freedom. That's basically the difference between the two. This has N minus D degrees of freedom. And if you add them up, you get N minus 1 because D is P plus 1 here. That's indeed the degrees of freedom of this, because if you remember, this is the SSE of M naught. You also know that the SSE of a model has degrees of freedom N minus the number of parameters. And the number of parameters here is just 1. So everything adds up. So this has to be number of parameters of M naught, which is equal to 1. DF equals. And then once you have this, you write it this way, and then you divide this by its degrees of freedom. This is called mean squared regression. And divide this by the degrees of freedom. This is called the mean squared error, or mean squares, or mean squares of regression, mean squares of error. And then the ratio is just the F statistic. So this is all just a tabular nice way of representing this data. And then the rest follows. Okay. So this is, as you can see, this type of ANOVA analysis is called ANOVA table is a very special case of the general test that we discussed already. Questions? You probably have seen this type of table or this type of analysis before, but hopefully you now understand where it all comes from. It's nothing special, it's just a special case of the development that we had so far. From this relation, you can see that if I divide both sides by SST, then I would get 1 is equal to SSE divided by SST plus SSR divided by SST. The ratio of SSR divided by SST, which is 1 minus SSE divided by SST from that identity, this is called R squared, or the coefficient of determination. And as I mentioned, this is this you can always think of as variation unexplained. Variation unexplained by M naught. This was SSE of M naught, and this is variation unexplained by the full model MP, the regression model. And the difference is variation explained. Explained by MP over M naught. Okay. And so the ratio of the variation explained by MP over M naught divided by the total unexplained variation by M naught, this is called coefficient of determination. So part of that unexplained variation in M naught is picked up by MP. So that's this part, and the rest is still unexplained. Okay, so the part that MP explains, the part of SST, or the unexplained variation left out by M naught, that's picked up by the regression model, is called the coefficient of determination. And this you can see is always between 0 and 1. The reason being that if you look at this, the sum of the two has to be 1 once they divide by SST, and both of them are positive or non-negative, so they have to be between 0 and 1. So the R squared measures the strength of the linear relation, how well the linear model does, or how well it sort of fits the data. It doesn't tell you about the sizes of the coefficients, so it could be sort of small or large. It just it tells you about the strength of the relation. Okay. So for example, you could have like it doesn't say, for example, the correlation is 1, or like so for example, if you have X and Y, and you have your data, it could be so in this model, if you have the same line but very tightly sort of scattered around this, R squared would be higher. Okay, it could be like exactly this, but could be the relation could be very small. So like there could be a linear model like that, the same sort of variation across this, the same sort of tiny little tank. The R squared would be like, the behavior would be the same. It doesn't matter whether the correlation is high or low. It's just that the strength of the linear relation is high. And so that's picked up by R squared. R squared of these two models should be roughly the same. Whereas in one case, the correlation is higher. In the other case, the correlation is lower. So it's just the noise relative to the linear relation. So if the noise relative to the linear relation is small, the R squared would be high. If the noise is too high relative to the linear relation, then this is going to be small. So it's a little bit like a subtle point. If R squared is 1, you can't say that the X and Y are perfect. Let's say if you have just a single X and a single Y, you can't say they're perfectly correlated. So the correlation could be still small, but relative to the noise, it's sufficiently good. So it's just a relative concept relative to the noise, relative to the unexplained variation. So the other point is that, so questions, comments? Yeah, everything clear? So the other comment is that whenever you add a variable, you always increase R squared. So whenever you add a variable to your model, you go to a super model, let's say. I mean, the new model would include the previous model. So it would be the previous model would be a submodel of the new model, or you can say that the new model is a super model of the previous model. So whenever you go to a higher level model that contains the previous model as a nested model, your R squared always increases. In other words, the SSE always decreases. And this is the relation that we saw before. So whenever you have, let's say, M1 nested within M2, we know that the SSE of M1 is bigger than or equal to the SSE of M2. And so the R squared of M1 would be less than or equal to the R squared of M2. So adding a variable would always let you go to a bigger model, because if I have like a model that has beta 0 plus beta 1 x1 plus epsilon, if I have a new variable included in the model, you can see what would happen. Let's say I have like a gamma z, new variables comes in, I want to include it in the regression. This new model M2 contains M1 as a submodel. So what would happen is that always the R squared would go up. So the SSE would go down, the R squared would go up, SST doesn't change. So SST, you can see, is dependent only on the response. SST is this guy, which is the variation in response. It doesn't include any information about the covariance. So the problem is, if that's the case, then we can't use R squared as a good measure to compare these two models. Because I know that I always get a better R squared. R squared bigger means better. So I can keep adding variables to the model until at a point where I include the number of variables in the model is one less than the total sample size. Sample size is n. I get n minus 1. Here d, which is p plus 1, would be just n minus 1 plus 1, which is just n. So d would be the total number of parameters would be n. And so I have a sample size n, and d parameters, I get a solution, and that would be a perfect fit. So your regression model perfectly would fit the data, and then R squared would be 1. But this is not necessarily a good situation. So this is a case where you would worry about overfitting, because what you'd expect is that some part of your data is noise. The samples are coming from a noisy model. And what this is saying is that in this case, y is going to be equal mu hat plus e is going to be 0. So residual will be 0. And so y is exactly equal to the fit of value. So your regression model perfectly fits every point. Regression model perfectly fits the data. But you know that this shouldn't probably be the case, because you know that your data is noisy. So part of the data is noise. If you're fitting to the data, you're fitting to that noise as well. So you'd expect that if you get more and more samples, this model is not going to perform well, because what you end up having is something like so why overfitting is not why overfitting is problematic, because you expect in a finite sample of size n, that part of the variation, part of the variability or variation in y is due to noise. So we don't want to perfectly fit the data. So for example, if you have like a linear model, your true model is actually, let's say y is equal to beta 0 plus beta 1, let's say a star, xi, and you keep generating from this for a certain noise level, you might end up with these points, let's say. Okay, so this is my data around this for a certain sample size. If I, so if we take, so here, let's say n is, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should put somewhere here. Say 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say 12. So n is 12. Suppose I keep adding, suppose if we pose a model like yi is equal to beta, so that's what I'm going to pose a new model, beta 0 plus beta 1 x1. I'm going to keep, so let's say this is, I'm going to write it in the vector form. Y is equal to this x1 plus epsilon. So we have beta 0 plus beta 1 x1 plus, I'm going to keep coming up with covariates. I'm going to go ask people to provide covariates. I'm just going to keep including all up to like n minus 1, xn minus 1. So these covariates are not in part of the data generation process. That was one of the other like this questions that came up. So the data is generated like this, but I'm posing this model. I'm going to fit this model. I'm going to go ahead and this is why I have this y, and I'm going to fit this model. I get beta hat, which is x transpose x inverse x transpose y, where x is just 1 and x1 dot 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 xn minus 1. So this is, in this case, n by n. And you're going to assume that's full rank. Then this problem is solvable. But you can see what would happen. So if this is the case, so it's full rank, invertible, because x is a square. If it's full rank, so let's say assume x is full rank. Assume x is full rank. Then x will be invertible because it's a square matrix. Before we can't do this. We couldn't do this because this would be like n by d, and d is much smaller than n. This rectangular matrices cannot be inverted, but in this case it's invertible. So, and I also have x transpose inverse. In general, it's going to be equal to x inverse transpose, and like A inverse, AB inverse would be B inverse, A inverse. So I can invert this. I can actually decompose this. You can't do it in general, but in this case, I can apply it to each term, and it would be like switching the two terms: X transpose inverse, X transpose Y. We actually don't need this, but X transpose is also invertible. So I'm going to use that fact here, and you can see that these would simplify. So you would get Y star. So you can see that this would be equal to the identity, because this is just the inverse of X transpose and then times the X transpose. So you get beta hat is equal to X inverse Y, and mu hat would be X beta hat, which would be X inverse Y, which is just Y. So you can see mu hat is equal to Y exactly. So when you do this, you would fit perfectly. So you're when you plot the fitted values would match this. And if you plot your regression function, which is going to be mu of yeah, it's hard to do it in this case, but these are the fitted values would match this. But you would expect this to be problematic. Okay, so you don't want to perfectly match this. You would like to recover this in this case, which is your model is not doing. And in general, let's say the overfitting is the case where you would have this situation and you would end up basically roughly fitting true of every point. Let's say if I do if I take, for example, how can I get these extra covariates? I can just construct them by powers. So this would be like x1i, and I can take this to be xi1 squared, and this would be xi to the n minus 1, xi1. So I have the single covariate that I had, and I just keep adding the powers of it. So this would be a polynomial. This would be like a polynomial in xi1, where the polynomial p beta is just beta 1x plus beta 2x2 dot 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 beta n minus 1 xn minus 1. So the one way to do it is that. Then if I look at my regression function, which is just like beta 0 plus beta 1 x1 plus beta n minus 1 x n minus 1 for a new data point. This is equivalent to like beta 0 plus beta 1 x1 plus beta 2 x1 2 plus beta n minus 1 x n or x1 n minus 1. So if I have a new data point, I can equivalently think of this as just applying it to a single data point. So that if you plot this, then this regression function as a function of that single data point would be a polynomial that passes through these. And so this is the bad situation. So if I drop the number of, so this is the overfitting case. So if you drop some of these covariates, so let's say higher order covariates, you might get something like this, a lower order polynomial. This is a better compromise. So in general, there is sort of a trade-off. So it could be that your real data is actually not generated. So your real data could be generated from beta 0 star plus beta 1 star x let's say x1 and then plus beta star 2x1 2. So this could be how your data is actually generated. So you would have like a quadratic term and then the data is around this. So if you fit a single regression with just yi equal, so if you pose this model beta 0 plus beta 1 xi x1i plus epsilon I, you ignore the second coordinate, you're going to underfit. You're going to fit like a regression through this. If you do with the second order, you probably get a good thing. If you go with a third order or fourth order, you might be like obtaining this. So there is like an optimal sort of trade-off between the complexity of the model. The fully complex model would like interpolate between all the points. We don't want that. And then if your model is complex, if you choose less of the covariates in the model, like in this case, you do this just this line. This is underfitting, so this underfits. Whereas this overfits. This is just right. So this one, the green one, which is like probably a quadratic, this is just right. So in practice, you don't know what the actual model is, the actual generating process is, and it might not be either of these models. But you try, without knowing this, you pose different models and you try to test it on your data and see on your data how do they perform. And if your model matches the true model, great, then that's the ideal thing that you want to do. But in practice, you don't know the true model. And in fact, the true data generating process might be very complicated. And all your models are going to be approximations of the true data generating model. And so you have to have some way of determining where to stop. So let's say if I want to do this polynomial expansion, at what point should I stop? Should I stop at this point? Should I add like more of these terms and so on? The idea of model selection is what we'll at the end of the course get to, and that helps you decide which one should I pick without knowing the actual truth. So if you're just given the data, should I go with this linear model? Should I add like another quadratic term? Should I add like the third order terms? Should I include more covariates from other sources? And so on and so forth. So the whole point is that the R squared alone is not enough. So if you just go with R squared, you're going to always end up, let's say if you're doing the polynomial regression like this, you're always going to go with the one that overfits, which is probably not what you want to do, because you'd expect that these are noise. So why this is not good? Because if I get more data, they're not going to be exactly lying on this, most likely. If they're generated from this, they're going to be hovering around the line, which is if they're generating from this, they're going to be hovered around the line. There's no guarantee that they're on this purple thing. And so that if I fitted the purple thing, when I'm trying to predict the new data points that come in, I'm going to make a huge error. Whereas if I stayed close to this line, if I fitted a linear model, then my overall error would be quite small. They're like, this is a little bit debatable though, but there are new sort of results in the statistics that suggest that maybe interpolation is not necessarily that bad, but at least the traditional idea is that the simpler model is better, at least for interpretation is better, and perhaps for prediction is better. The prediction part is quite interesting recent developments that suggest that maybe for prediction it might not matter in some cases. But as long as you care about the actual model, this is far from the actual data generating model. So if you're trying to figure out the true model, assuming that there is a true model, then you have to somehow figure out a way to balance the complexity of the model with the fit of the model. So a model that just fits a linear regression is a more simple model. So just includes beta 0 and beta 1. It has two parameters. This polynomial model has like n parameters, which is way more complex. So you have to figure out at what point you have enough complexity and the fit is good. Part of this is it can be done by the F test, for example. You can do a sequential F test and test like this model that includes these two against the super model that includes the tree. And if you don't reject, you stay with this. If you reject, you go to this model, and then you add another term and then test. And so this sequential way is one approach. There are other approaches as well that at some point we're going to discuss. Okay, so I think I'll stop here at this point. This was an interesting discussion. I wasn't planning to go into details of this, but do let me know if you have questions right now or maybe later. Okay, this was an important issue that came up rather unplanned. Questions? Okay, if not, let's stop here. Thanks for coming, and hopefully we'll continue next week. Okay, see you. Thank you. Bye-bye.
Thank you.